let's understand the formula related to induced EMF. If rod is rotating in the uniform magnetic field, in that case, after that draw the electrical equivalence and find current in resistance capital R. Dear students, welcome to LN Overseas. Let's continue our special series. This series will cover 45 important topics in 45 days. It will be really helpful for all the JEE Main aspirant. This is the distribution of topics in physics, chemistry and mathematics. I'm going to cover physics part. So let's begin with the topic Motional EMF. This is very important topic for JEE Main examination. This topic is from Electromagnetic Induction. So before starting Motional EMF, we should know about the Faraday's law of electromagnetic induction. So what is this law? According to this law, the induced EMF in a coil is proportional to the negative of the rate of change of magnetic flux. I think you must know, whenever we are changing magnetic flux related to any closed circuit, then EMF will induce in that closed circuit. That EMF we called induced EMF, right? And we can find that induced EMF by Faraday's law of electromagnetic induction. We can write E is equal to minus d phi by dt. Right, students? You can say, sir, why you are using negative sign? This negative sign is because of the Lenz's law. By the Lenz's law, you can find out the direction of induced EMF. What is this law? According to this law, the direction of induced EMF in such a way that it opposes the cause due to which it is produced. So that's why I'm using here negative sign. Here this is d phi by dt, rate of change of magnetic flux. Right, students? So to understand motional EMF, we have to remember this and we have to modify this one, right? So let's understand what is motional EMF, right? You can see here, this is a rod, right? And this rod is moving with v velocity, and this is the inward magnetic field. I am representing this by b vector. This is inward, okay? And the length of the rod is given, this is L, and this rod is moving in this direction. According to Faraday's law of electromagnetic induction, induced EMF is equal to rate of change of magnetic flux, right, students? But here this rod is moving, right? According to Faraday's law, we can write E is equal to d phi by dt. I am writing only magnitude, right? So flux is changing here. But here, this rod is cutting flux. So we have to modify this. E is equal to flux cut divided by time taken. So if this rod is moving in uniform magnetic field, right, and this rod is cutting flux, so in this rod, EMF will induce. That EMF we called motional EMF. Why? Because that EMF induced due to the motion of the rod, right, students? So let's understand the formula related to induced EMF. Just see here, let's suppose this is a rod, right? And this rod is moving with v velocity, right? And this is the magnetic field which is inward, right? And this rod is moving in inward magnetic field with v velocity, right? Right? Let's say this is the position of rod at any time t. Okay, after dt time, what will happen? This rod will travel some distance, right? And let's say this is the position of rod after dt time. Okay, is that clear? So I am writing t plus dt. And in that period of time, this rod is covering some distance. That distance we can write v dt. Right, students? So you can see here, this rod is cutting this much flux, right? Is that clear? So according to Faraday's law of electromagnetic induction, we know that E is equal to d phi by dt, and we modified this in flux cut divided by time taken. You must know formula for magnetic flux, that is A dot B, right? So E is equal to A. This area we have to find. So area is length into breadth. So let's take this length is L. So L into this. Okay. So L into V dt, and magnetic field is B, right? This is our flux divided by time. So dt cancels. So E is equal to VBL, right, students? So this is the formula, right, by which you can find out induced EMF. But you can say, sir, how can we find out the polarity? So for polarity, we have to understand one more concept, that is induced EMF by Lorentz force. So let's understand. You can see here, this is the rod of length L and it is moving in uniform magnetic field with V velocity. Magnetic field and velocity vector both are perpendicular to each other, right? Now see, this rod is conducting rod. So there are so many free electrons. Okay, I'm representing only one free electron. Okay, students, right? So if I write this is free electron, and this electron is moving in this direction with V velocity, right, students? And magnetic field is inward, right? So this magnetic field I am representing by cross. It is inward. I think you must know, whenever charge particle moves in uniform magnetic field, then that charge particle will experience force, right? How can we find out that force? I think you must know. Force formula is Q V cross B. Q is the charge, V is the velocity, B is the magnetic field, right, students? So that formula is, in vector form I am writing Q V cross B, right, students? Okay, so this is electron. In which direction this force will act? So direction of force we can find out by the direction of V cross B, right? V in this direction, stretch your finger into the direction of velocity and curl your finger into the direction of magnetic field. So thumb will show you direction of force acting on the charge particle. Sir, here this is electron and on electron force is acting in upward direction. No, we have to use negative sign also because this is vector. So your force is not in this direction, your force is in this direction, right? Is that clear? If you write magnitude of force, so magnitude of force is E V into B, because V cross B is VB sine theta and angle between V and B is 90 degree, sine 90 is 1. So E V B, this is the magnitude of this force, right, students? I am giving this force name 1, right? You can say, sir, on electron force is acting in this direction. So what will happen? These electrons will move in downward direction, right? So this end of the rod will acquire, if electrons are moving in downward direction, right? They will acquire, this end will acquire negative charge, right? And this will acquire positive charge. So charges will induced. Is that clear, students? Okay. So you know that you can say, sir, charges are inducing. Then electric field will also induce. So that electric field will also induce in this direction. This electric field is your induced electric field and direction is like this. You can say, sir, there is electric field, then this charge must experience one more force because of the presence of electric field. Yes, it will experience. That force is in the direction of electric field on the positive charge. This is negative charge. So on this negative charge, this force will act opposite to the direction of electric field. So force will act in this direction. I am giving this name F2 and force formula is Q into E, charge into electric field. So charge is E, charge on electron, and this is the magnitude of electric field. Is that clear? Initially, the magnitude of this force is more than the magnitude of this force, right? So charges will move in this direction, right? After some time, what will happen? This force, they are moving in this direction. Charges are increasing, induced charge is increasing. So what will happen? Electric field will increase. This force will also increase, right? So at electrostatic condition, net force on the electron will become 0. Is that clear? After that, no charge will travel. Are you getting my point? So we can equate these two forces. So E into E is equal to EVD. This E cancel. So E is equal to V into B. Is that clear? This is the induced electric field. You can say, sir, this is induced electric field. So if there is electric field, then we can easily find out potential or EMF because of this electric field. Yes. What is the relation? Relation is this: delta V is equal to E into L, right students? Length is L. Are you getting my point? So E is V, B and length is L, right? So this is the magnitude of your induced EMF in the rod. You can say, sir, we already derived this formula. Why you are deriving again? Because by this derivation, by Lorentz force, you can find out the direction of induced EMF, means polarity. How? By V cross B. Okay. So this end, you can see I explain everything. This end of the rod will acquire positive charge. This end of the rod will acquire negative charge, right? So you can replace this by a cell, right? This is positive polarity, this is negative polarity, and EMF is VBL. And you can find direction by V cross B. V in this direction, right? And B is inward, so thumb will represent direction of positive polarity. So always keep in your mind, okay? So I'm writing here V cross B will represent direction of positive polarity, and formula is VBL. Okay, right students? You can say, sir, you are taking a straight rod, you are taking a straight wire, right? If I give you any random shape wire, in that case, how can we find? Let's find. So next case is motional EMF for random shaped wire. You can see here, this is random shaped wire and magnetic field is inward, right? How can we find induced EMF in this random shaped wire due to the motion? Let's find. See here, I am taking this small element of the wire, right? So I am drawing here, this is the element, right? Cylindrical wire, and you know that in this wire there are so many free electrons, right? I am representing only one electron, and this is V, right? Velocity with which it is moving in this direction. Magnetic field is given inward. Although if magnetic field is at any direction, you can find. Okay, so I'll derive generalized formula. Okay, this formula will help you for tough type of question. Okay, so you know that, sir, it is moving, so it will experience, we already find V cross B. This will experience force in this direction, right? That force I am using F1, right? F1 is Q into V cross B, right? Okay, so Q is E. Now you have to put with negative sign because you are writing vector form. So F1 is equal to minus E V cross B, right students? Okay, you know that because of this, this will acquire negative, right? And this will positive, induced charges. Because of this, in this direction, electric field will induce. That electric field I am naming induced electric field, right students, in this direction. Okay, due to this electric field, this negative charge will experience force in this direction. That I think you all know, Q into E vector, right? This force I am giving name F2, and I am writing F2 is Q into E, and Q is minus E. So with sign you have to put minus E into E. And at the electrostatic condition, when these two forces are equal, in that case, net force on the charge is 0, on the electron is 0. So net force you can write F1 vector, this is vector, this is vector, vector, right? F1 vector plus F2 vector is 0. Okay, so F1 is minus E V cross B, and F2 is minus E into capital E is equal to 0, right? Let's solve. So minus E V cross B is equal to E capital E, right? This E cancel. So you can see here E vector is equal to minus V cross B, right? This is your induced electric field. If there is induced electric field, then you can easily find out potential difference, right students? So let's find. See, induced electric field is minus V cross B, and there is relation between potential and electric field, minus E dot dl, right students? Okay, yes or no? This negative sign is only representing if you are going into the direction of electric field, then potential will decrease. Okay, you must know that this. So E is, let's put minus V cross B vector, right, dot dl vector. Okay, this is your small induced EMF, right? But we have to calculate total, so we have to integrate. So let's integrate. So this is your induced EMF, minus minus plus, integration V cross B dot dl vector, right? Let's see in this diagram. V is constant, magnetic field is constant. Okay, so I am taking V cross B outside the integration. So V cross B vector, integration dl vector and dot product, right? What is this? This is small length, this one, dl vector, right? This is dl. Okay, so what we have to do? We have to add all these small dl vector like this, like this, like this. And how can you add? This is vector, we have to use polygon law. So this is the tail and this is the head of the vector. Okay, so this will give you resultant of all these addition of small dl vector, right? This is your L vector. Okay, at this tail, at this head. Is that clear? So I am replacing this with V cross B vector dot L vector. So this is your induced electric field. So this is your induced EMF. This formula you have to keep in your mind, right students? Let's learn some different cases related to this induced EMF. You have to remember all these formula. These formula will help you in direct formula based questions. So you can see here some cases. So first case I'm taking this one, right? We already derived this one. This is conclusion. So you have to remember formulas. This is a straight wire of length L. It is moving with v velocity in the perpendicular magnetic field. Velocity vector and magnetic field vector are perpendicular to each other. In that case, induced EMF is BVL. Is that clear? You have to remember this formula. Okay. So when length, velocity and magnetic field are perpendicular to each other, then induced EMF, remember, E is equal to BVL. In second case, you can see wire is moving like this. Okay, so here this is your length vector, right? This is your velocity vector. They are parallel to each other. Okay, so you can see here length, velocity are parallel to each other. If any two quantities are parallel to each other, in that case, induced EMF is 0. Is that clear? There is no flux cutting by this rod, so that's why E is 0. Now, you can say, sir, if rod is moving at any angle, in that case, how can we find induced EMF? So you can see here, this rod is moving at an angle theta. In that case, induced EMF is BVL sin theta. You have to remember all these cases. Is that clear, students? Now, next, if rod is rotating in the uniform magnetic field, in that case, how can we find induced EMF? Okay, so let's solve this one. You can see here, this is the rod and length of rod is L, right? And cross is representing here. So cross represents inward magnetic field, right? This rod is rotating with angular velocity omega. In that case, sir, will EMF induce? Yes, it will induce, because if rod is moving like this, so it is cutting flux. So if it is cutting flux, then EMF will induce. So how can we find? Let's see. This is omega. So if this is the center of the rod, center of mass of the rod, So this center of mass of the rod have some velocity. Similarly, different points on this rod have different velocity. Why? Because I think you all know V is equal to, if omega is given, right? And if distance is given, this is hinge, and from this point to this point distance is x, so V is x omega, right? If x is changing, in that case V is also changing. So in that case, what we have to do? We have to take element, right? So what I am doing? I am going at x, right, like this, and taking a very small element of dx length, right? Okay, and if I draw the direction of velocity, so velocity will be in this direction, and velocity you can write v is equal to x omega, right? You can say, sir, why you are writing velocity? Because you know that E is equal to VBL when magnetic field vector and velocity vector perpendicular to each other. You can see magnetic field vector is inward, velocity vector is in this direction, they are perpendicular. So we have to use that formula. Okay, students. So in this small element, if you calculate induced EMF, so induced EMF is dE is equal to, you know the formula, VBL, right? So dE is equal to V. V is x omega, B is B, and L is length. Length is dx. Is that clear? Okay. Sir, what about direction? Direction will represent by V cross B. So stretch your finger into the direction of V and curl towards B. Okay. So thumb will represent direction of positive polarity. Okay. So if I represent this small element here, so you can see here, this is your small element, right? This is the hinge and omega, and this distance is x, this is dx. Okay, so this end behave like a positive polarity and this end behave like a negative polarity, right? Is that clear? And this is small d, small induced EMF d, right? Okay, now we have to find out total induced EMF in this rod. So what we have to do? We have to take these small element from this point, right, 0 to L, and we have to add all the induced EMF, right, students? So for total induced EMF E, let's integrate dE, right? So integration from 0 to L, omega B x dx. So omega and B are constant, you can take out from the integration. So omega B and integration x dx. Integration of x dx is omega B x square by 2. Limits are 0 to L. Now put the limits. So it's omega B L square by 2, or you can write like this, B omega L square by 2. So this is the formula which you have to remember if rod is rotating with angular velocity omega in uniform magnetic field. So this is the formula for induced EMF, and you can represent this rod by a cell, and induced EMF is B omega L square by 2, right? So we learn many formulas related to induced EMF. Now let's apply all these formula. So I will take some questions. So question 1, you can see here, let's read first. A rectangular loop as shown in the figure moves away from an infinitely long wire carrying a current. Okay, so this is infinitely long wire, this is carrying a current. I. Find the EMF induced in the rectangular loop. This rectangular loop is moving with constant velocity. Okay, sir, where is magnetic field? You know that whenever current is flowing in the conductor, then it will generate magnetic field. We have to find the direction of magnetic field by using right hand thumb rule, right? What is right hand thumb rule? Place the wire in your right hand in such a manner that thumb represent direction of electric current, then the direction of finger curl will represent the direction of magnetic field lines. Okay, and in the direction of magnetic field line, magnetic field is. Okay, so magnetic field lines are like this. So magnetic field is invert. Okay, so I am representing magnetic field here by cross. Okay, cross. And sir, what is the formula for magnetic field? You have to write formula first. So due to this infinitely long wire, magnetic field is mu naught I upon 2 pi r, right? If r is any distance. Okay, students, right? Mu naught I upon 2 pi r. Sir, r is changing, so this is changing. Yes, it is changing. Do we have to integrate? No need, because you can see here, this is, you can consider this one rod A. I am representing by PQRS. Okay, so P, Q, R and S. You can consider this as a separate rod, this as a separate, this as a separate, this as a separate, right? Induced EMF due to these two rods, 0, because velocity vector and length vector both are perpendicular to each other. Only this part and this part are moving perpendicular to the direction of magnetic field. Is that clear, students? So because of this, induced EMF will be there. And what about direction? V cross B. So V in this direction, B is inward. This is your B vector. Okay, B vector. B is inward. So direction of induced EMF means direction of positive polarity is like this. So I am representing this by E1. I am giving name E1, right? And let's say some resistance of this wire I am representing by R1. Okay, similarly 0, but it will have some resistance, let's say small r2. And for this, again same, this is positive polarity, this is negative polarity, this I am giving E2. Okay, and some resistance, and this will also contribute in the resistance. So this is R3, this is R4. So this is circuit diagram. Okay, so now let's find E1. E1 is, formula is VBL, right? Okay, V is given, B is this, right? At this point, distance is x. So B you can write V mu naught I upon this length is x. So 2 pi x, and length of the wire is capital L. Is that clear? After that, E2. E2 is again V B2 into L, right? So B2 we have to find. This length is x plus B, right, students? Okay, so you can write here V mu naught I upon 2 pi x plus B into L, E1 and E2. You can see here, E1, this length is less, so E1 is more. Okay, so net induced EMF, if you write, so net EMF is E1 minus E2. Now you have to put the values. So V mu naught I and L I am taking common. So mu naught I V into L divided by 2 pi is also common. Remaining terms are 1 upon x minus 1 upon x plus B. Right, students? Okay, now solve this. So E is equal to mu naught I V into L divided by 2 pi, and LCM is x plus B, right? If you take LCM, then it will become x plus B minus x. So this cancels. So E is equal to mu naught I V L divided by 2 pi and B x plus B, right, student? So this is your induced EMF for that circuit, right? Now let's take next question. So question is, a rod of length capital L and resistance small r rotates about one end as shown in figure. So this OA is rod, right? Length of this rod is given capital L and it is rotating with angular velocity omega. Its other end touches a conducting ring. So this is a conducting ring and this end is touching this conducting ring. Of negligible resistance. Resistance of this ring is negligible. A resistance capital R is connected between center and periphery. So this is capital R. After that, draw the electrical equivalence and find current in resistance capital R. There is a uniform magnetic field B directed as shown. So you can see here, magnetic field is this, right? Cross represent inward magnetic field. Okay, and this rod is rotating in this inward magnetic field. Magnetic field is everywhere. Okay, like this, right, students? I think you must know, we learn formula whenever we rotate any rod in a uniform magnetic field, then EMF will induce in that rod. And what is the formula for induced EMF? Induced EMF is B omega L square by 2, right? Okay. And sir, what about direction? V cross B will represent direction of positive polarity. Keep in your mind. So V is in this direction, magnetic field is inward. So V cross B. So this is direction of positive polarity. So if I draw diagram, so you can see this is positive polarity E, right, is equal to B omega L square by 2. Right, students? And resistance is given small r. So you have to draw equivalent circuit diagram. So this is a small r, right? This is the ring, right? And if I draw like this, so this is O, this point is A, this is E, and this is D, and here is the resistance capital R, and this point is C. Right, students? You can see here, this is zero resistance wire. So this point, this point, this point, this point, they are at same potential, right? This point and this point is also are at same potential. So how can we solve this question? Just see. So this is the circuit, this is resistance, and this point is O. So I am representing this R, and this is like this, and this I am representing like this. Okay, this point is A, this point is C, right? This somewhere here E, right, students? Okay, there is no need to represent D. Okay, and this is E, B omega L square by 2. This is a small r. These two are also at same potential, so you can draw diagram like this. This point is O. Okay, so like this, E is equal to B omega L square by 2, right? And this is a small r, and they are at same potential, so you can join these two also. So this is R, capital R, this is a small r, and current will flow like this. We have to calculate current. So how can you calculate current? I think you all know, according to Ohm's law, V is equal to IR, right? Ohm's law. So V is B omega L square by 2. R is R equivalent. These two are in series, so R equivalent you can write capital R plus small r. So your current is B omega L square by 2 R plus small r. So this is the answer for this question. Hope you all understood all the concepts related to motional EMF. That's all from my side on this topic. Don't forget to watch our complete series. The playlist link is given in the description box. Still, if you have any queries or suggestion, feel free to reach out to us. For more, stay tuned. Thank you.